Hi there, folks. Today we're looking at simplifying radicals, but only from a numeric perspective. We're going to simplify these things. We're going to leave them in terms of radicals, but we won't involve any variables just yet, okay? So you probably already have a very limited view of this so far. You've probably looked at square roots in the past. Now we're going to expand that to things like cube roots or fourth roots and just kind of generalize all the different radicals that we could have here. All right. There are two methods for simplifying a radical. One of them is building a factor tree and using the prime factorization. That's an okay way to do it, but we want to use something that's a little bit more sophisticated, so we're going to use perfect roots to do this. Okay, so if we're talking about a square root, we're going to look for perfect squares. If we're talking about a cube root, we'll look for perfect cubes and so on and so forth. So simplifying radicals using perfect roots. Just a reminder of some of our perfect square numbers, and you probably have a bunch of these memorized. But 1, 4, 9, 16, these are all values that we can take the square root of very easily and very readily without the use of a calculator. We all know that the square root of 1 is a 1. The square root of 4 is a 2. The square root of 9 is a 3. The square root of 16 is a 4. Okay? And the reason that exists is because this is essentially 1 squared. This is 2 squared. This is 3 squared, 4 squared, 5 squared, okay? That's where these numbers come from. They're something squared, but that's also how the square root works. It's undoing the squaring process, okay? So undoing squaring of 5, so the 5 squared is a 25. When I undo that, when I take the square root, it brings me back to the 5, okay? So like this one, this brings me back to a 6 because 36 was the 6 squared, okay? 49 brings me back to a 7 because that was 7 squared. Okay, that's kind of what roots do, is they do the opposite of raising something to a power. Okay, and so we're kind of working backwards in that regard. All right, so when we do this, we're going to look for these values. We're going to look for these values within the number we have. Okay, so we're going to look for things like 9s or 16s or 25s. All right, so we're going to find perfect roots that divide evenly into the radicand. That's a big word. Radicand is just the number under the square root. Okay, so the radicand is the number, or in this case, under any root. And if you just want to say that, okay, that divides evenly into the number under the root, all right? And then we're going to take the root of each perfect root, okay? See, once we break this up, like if I have a 25 in there, well, I know how to take the square root of 25. It's a 5, okay? For example, if I look at something like this guy, right here, I've got the square root of 8, and I want to think about that list of perfect squares and ask myself, are there any perfect squares? Are there any numbers from that list that divide evenly into 8? And remember, here was my list of numbers. Okay, and we could keep going with that, all right? So I'm just asking, are there any of these numbers? Do any of these perfect squares divide evenly into 8? And hopefully you can look through here and say, well, yeah, the 4 divides in there. So here's what I do. I rewrite this as the square root of 4 times 2. That's what 8 is. It's 4 times 2. But now essentially I'm just going to take the square root of each of these individually. Like if I were to kind of think of this off to the side for a moment and just say, hey, if I had the square root of 4 and then separately I had the square root of 2, well, you know how to do one of those right here. This guy, the square root of 4 is just a 2. So that's just a 2. The square root of 2, I don't know what that is, so I just leave it the way it is. All right, and that's essentially what we're doing down here. We say, hey, the square root of 4, well, that's a 2, so I write a 2 down. But then when I take the square root of 2, I can't really simplify that. I just leave it as the square root of 2. Okay, that's the idea, is we're basically just breaking this thing down into stuff we know how to do. I know how to take the square root of a 4, so I break this thing down into a 4. Okay. If I look at the next one, same kind of thing. I start looking across this list, and usually the first one that students come across here that they know divides into a 72 is the 9, okay? So students do this. They say, okay, 72, that's 9 times 8. And they say, okay, I know the square root of 9. The square root of 9, well, that's a 3. So they pop that 3 out there. But then they say, okay, the square root of 8 I don't know, but look at the previous example. I just did the square root of 8, and I broke that down into a 4 times 2. So I keep going. I look for more perfect squares. And then I say, oh, yeah, the square root of 4, well, that's a 2. And keep in mind, right now, this is negative times. So there's multiplication written right here. So it's negative 3 times that square root. So it just pops out, and now it's still times 2. So that 4 became this. And then the square root of 2 that's left just stays underneath there. So now I have negative 6 root 2. Okay? So I'm just breaking this thing down into stuff I know how to take the square root of. And as I come across things that I know how to take the square root of, I take the square root of them and then go on the outside. All right? And it's still the same operation. Notice the 72 broke down into 9 times 8. It's multiplication. The 8 broke down into 4 times 2. It's multiplication. On the outside, when it comes out, it's 3 times 2 on the outside. It's a negative 6. But now here's the kicker. I could have made this a little bit easier on myself. All right? There's actually a larger perfect square that divides evenly into 72 right from the start. And as you're looking through that list, maybe you can identify it. But it's this one. It's 36. That's 36 times 2. And see, now watch what happens. I can take the square root of 36. The square root of 36 is a 6. And now the square root of 2 just stays as the square root of 2. I don't know how to do that one. And notice I got the same answer, but with a little less work. And the moral of the story there is basically if you can find the largest perfect square, you should be able to do this one step. Okay? If you don't see the largest perfect square, that's okay. You just keep looking for perfect squares. You keep taking the square root of stuff you know how to take the square root of until you run out of things that you can take the square root of. Okay? If I look at the next one, same kind of thing. I start looking through here, and maybe you recognize that 4 divides evenly into that, or that 16 divides evenly in that. But keep going. Try to find the biggest thing. And I don't actually have it written here, so you might have to think about that list a little more extensively. But the largest perfect square that goes in here is 64. This is 64 times 2. And now from here, the square root of 64, well, that's an 8. The square root of 2, well, I don't know how to take the square root of 2, so I leave it as the square root of 2. Okay? If I can't do it without writing a decimal, then we don't do that one. We're trying to simplify these just using perfect squares, only simplifying things that come out nicely. Okay? And here's the thing, the other option here, which I kind of shy away from, is, I'll do it over here with the 8, is using your factor tree when you say, oh, that's 4 times 2, and then that's 2 times 2. And so the prime factorization, I always extend this branch so I can see it. It's 2 times 2 times 2. And then you circle the pair and say, hey, here's a pair of 2s, so that goes on the outside as a 2. The lone 2 stays on the inside. Okay? And there's nothing wrong with that method. It's more literally showing that you're undoing something squared. Like the pair of 2s is 2 times 2. You're undoing 2 squared and getting a 2 on the outside. Okay? And you could do the same thing with 72. You could do the same thing with 128. But those factor trees become really long and really extensive, and it becomes really cumbersome to be able to do that. All right? So 1, we cut down on the amount of stuff we have to write. All right? And 2, this process, looking for perfect squares, is one that we can eventually start to do in our heads. Like the square root of 8, I can immediately look at that and say, oh, 4 times 2, square root of 4 is a 2, the other 2 is still trapped. 72, oh, it's 36 times 2, the square root of 36 is a 6, the 2 is still trapped, okay? And so we can start to convert this to a mental process. Just like when you first learned addition and subtraction, you probably used your fingers to count those things out quite a bit. You don't do that as much now. You've converted it to a mental process. It's something you can do in your head. By doing it this way, eventually you'll be able to do this in your head, okay? If I look at this one, and again, if I were doing this in my head, I'd probably look at it and say, oh, 75? Well, that's 25 times 3. The square root of 25 is a 5. The 3 is still trapped. So then what I end up with is 4 times 5 times the square root of 3, so it's 20 root 3. Okay, see, I just did that whole thing in my head, all right? But now let's see the work that would be written down with this thing. So again, I look at this and say, okay, 75, that's 25 times 3. And again, the reason I chose 25 is because I know how to take the square root of 25, okay? The square root of 25 is a 5. So I have a 4. I now also have a 5 because I took the square root. And then the square root of 3, I'm not sure what that is. So I can't do that one in my head, so I leave it as the square root of 3. And then I multiply what's on the outside, okay? And again, this is multiplication, so anything that comes out of there is still multiplication, all right? If I look at the next one, again, I'm looking for perfect squares that divide evenly into this. And, you know, part of the problem with this is maybe our number sense is not perfect or not great, all right? You might have to do a little bit of guess and check here, okay? Consult the list that we had earlier and start plugging things in. The first one you're going to come across is maybe a 4, okay? But now think about that for a second, and let me scroll back up. If I have a 4 that goes into this thing, all right, well, if I want something bigger, that makes 16 probably a decent candidate, okay, because 4 is part of 16. Or even 36 a decent candidate, because 4 is part of 36. So look for those relationships between the numbers. So this one, you might see the 4 first, but if you go up a little bit higher, you're going to find a 16. Okay? You're going to find that 96 is 16 times 6. And now I know how to take the square root of 16. The square root of 16 is a 4. The square root of 6, well, that's just the square root of 6. I can't simplify that one. Okay, so it stays as a square root. All right? If I look at the next one, again, I start looking for perfect squares. I think the only one that goes in here is a 4, so 4 times 6. And now I take the square root. The square root of 4 is a 2. So I had a 3 out here. I now also get a 2. And now the square root of 6 is just the square root of 6. I can't simplify that any further. So now I end up with 6 root 6. Okay? But again, this is a process that you can start to try doing in your head. And one of the things I would try is, try doing it in your head. See what you get, and then go back and show your work to see if that answer matches. Okay? You might surprise yourself with how good you get at these when you start trying to do these in your head. But again, it's about identifying those perfect squares. Okay? If I look at these fractions, we just take the square root of each of these individually. So if I have the square root of 49 over 25, that's the same thing as saying the square root of 49 over the square root of 25. I just take the square root of each of those individually, okay? The square root of 49 is a 7. The square root of 25 is a 5. And that's it, okay? If I look at the next one, same kind of thing. The square root of 32 divided by the square root of 81. But now from here, unlike the last one, 32 is not a perfect square, so I start looking for perfect squares that divide evenly into 32. And the first one I stumble across is a 4, but maybe I try to go bigger, so I try 16 next, and I find that that works. Okay, 16 times 2. And so now up here, the square root of 16 is a 4. The square root of 2 is just the square root of 2. Underneath, students will sometimes break this up into a 9. They'll say, oh, 9 divides in there. Well, 81's already a perfect square. Do I need to change it if the thing's already a perfect square? That's something I already know how to take the square root of. The square root of 81 is just a 9, so I put a 9 down, okay? I don't have to break that one up any further, and now that's it, okay? All right, so here, simplifying larger radicals using perfect roots. It's the same directions as before. We're going to look for any perfect roots that divide evenly into the radicand. So we're going to break this up into things that we can take the root of. The difference is instead of a square root now, I'm looking at cube roots, or maybe I'll look at fourth roots, okay? Just to give you an idea what these looks like. So here are perfect cubes, and you probably don't have this list memorized, okay? But it's an easy list to construct. Think about how we constructed perfect squares. 1 squared was 1. 2 squared was 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. That's where those values come from. And it's the same thing here. 1 cubed. 2 cubed. 3 cubed. And I put this down because it helps us kind of not only see where these come from and how we could kind of construct this list on our own, but it also helps us to see the cube root of those things. Like if I said, hey, the cube root of 1, well, that's right here, it's a 1. If I said the cube root of 8, well, that's right here, it's a 2. The cube root of 27 is a 3. The cube root of 64 is a 4. The cube root of 125 is a 5. The cube root of 216 is a 6, okay? The cube root is undoing cubing something, all right? So when I take a perfect cube, it works me back to the thing I was cubing, all right? And so when we look at this, the only difference here between square roots and cube roots is now instead of looking for perfect squares, I'm going to look for perfect cubes. I'm going to look at this particular list. And so if I looked at this particular number, the cube root of 128, I'm looking for perfect cubes that divide evenly into 128. And you might look at it and say, well, does 8 go in there? And you might try that out, and you're going to find out that it doesn't work, okay? You might not be sure. You might have to test it. 27, try dividing 27 in your calculator, okay? You'll find that that doesn't work either. The one that works is the 64. And so I break this up. It's the cube root. This is 64 times 2. And so now I take the cube root of 64. And be careful here. We know the square root of 64 is an 8, but the cube root of 64 is a 4. And again, if you're not sure about that, go back up to this list, okay? Think about the cube root of each of these. The cube root of 1 is a 1. The cube root of 8 is 2 because that's how we got the 8. It was 2 to the third power. The cube root of 27 is 3 because that's how we got the 27. It was 3 to the third power. The cube root of 64, that's the one we just did. It's 4 because 4 to the third power is 64. Okay, that's where these values are coming from when I take the cube root. Okay, and really the toughest thing about cube roots, and I think the thing that makes them the most difficult, is we haven't dealt with those numbers as much. We don't have cube roots memorized. All right, and so we get a little bit mixed up with our square roots because that's what we're familiar with, okay? It's a little bit harder to identify because we don't have the numbers memorized, and it's a little harder for us to take the cube root because, again, we're so locked into square roots, okay? If I look at the next one, same kind of thing. I want the cube root of 24 here. Well, I just look for numbers from this list. The first one I see is an 8, and I think that's the biggest. It's 8 times 3. And so now I take the cube root. The cube root of 8 is 2. So this is 3 times 2. All right, I already had a 3 out there. Now I get another 2 out there. And now the cube root of 3, I can't simplify that any further. It stays as the cube root of 3. So now this becomes 6 cube root of 3. All right, but this is how all roots work, okay? This guy, same kind of thing. I start looking through that list. And in this particular example, I think the biggest one is still an 8. I don't think we can go any further than that. And again, that might take a little bit of guess and check on your part. That's 8 times 12. And so now the cube root of 8, we already discussed this one earlier. The cube root of 8 is 2. The cube root of 12, I can't simplify any further, so it just stays as the cube root of 12, okay? And so after I break this up, I just take the cube root of each thing until I've run out of stuff, okay? The cube root of 8 was 2. That was easy. That I could simplify. But the cube root of 12, that's just the cube root of 12, okay? So now let's think about it. Let's think about perfect fourths. If I wanted to take fourth roots, and we're not going to do a bunch of these, okay? I just want you to understand the concept. And see, I don't have my perfect fourths memorized. I'm really sad to say, I'm really ashamed of myself. So here we go. 1 to the 4th power, well, that's a 1. And now I can find 2 to the 4th power. Well, that's a 16. See, I'm creating a list of perfect fourths. 3 to the 4th power. Well, that, my friends, is an 81. Sorry, selected the wrong color. 4 to the 4th power. Where's my... Oh. Sorry, I keep going the wrong color. 4 to the 4th power is 256. Okay? And I only know that one because 4 to the 2nd power is 16. I know 16 squared is 256. All right, it happens to be the same thing. If you have no idea what I'm talking about, that's okay. 5 to the 4th power, that's a 625, okay? And so on and so forth, and it keeps going. All right, I think that's a big enough list. But now as I look at perfect fourths, if I'm on the 4th root, I just consult this list. And if I look at this list, like for this first one, the biggest number from this list that divides evenly into 128 is going to be the 16, okay? It's 16 times 8. And now, again, consulting this list, the 4th root of 16, I can see it right here. The 4th root of 16 is right here. It's a 2. So the 4th root of 16 is a 2. The 4th root of 8 just stays as the 4th root of 8. Okay? But this is how all roots work. I consult this list. If I look at the next one, I'm looking for a perfect fourth that divides evenly into 24. Well, as I look across this list, there isn't one. Okay? This one literally can't be simplified anymore because I don't have anything from that list that can go into this guy. So I just say, hey, there it is, done. Okay? The next one, same kind of thing. That's a 16 times 6. And once again, the 4th root of 16 is a 2. Again, we don't come across 4th roots a lot, but I want you to understand that the concept is the same. I look for a perfect version of that root, and then I can take the root of that particular number. Okay, with square roots, I look for perfect squares, and I take the square root. With cube roots, I look for perfect cubes, and I take the cube root. Okay, and again, when we get to things like 4th roots, the thing that makes them difficult is I don't have this list memorized, okay? This list is not on the tip of my mind or the tip of my tongue here, okay? I have to construct the list. I have to really think about it, all right? With perfect squares, there's less thought because we've been dealing with those for a long time, okay? One more thing we're going to look at today, we're going to look at imaginary numbers. Oh boy, everybody's favorite, imaginary numbers. Numbers that aren't real in any way, shape, or form, Okay, so imaginary numbers, in the past, if you tried to take the square root of a negative, your calculator gives you an error message because it can't be done in a real world sense. Okay, and in the past, you've written things like no solution or can't be done or this is impossible. All right, but now that we're in Algebra 2, we're going to go a little bit more abstract with this. And we're going to say, hey, that the square root of a negative gives us the number I, and that is a lowercase cursive I. When I write them, I write them like this, okay, the little banana peels, okay? And so I have my little banana peel with the dot, that's an I. So a cursive I represents an imaginary number, okay? So the square root of -1 is defined as equaling I. For example, if I look at something like this guy, if we just add -1 to our list of perfect squares, this is how we can kind of do this thing. We would say, hey, you know what, 64, that's a -1 times 64. And I'm going to start with the thing that's familiar to me, the square root of 64. The square root of 64 is an 8. And now the new thing I just taught you is that the square root of -1, the square root of -1 is an I. So it's 8I. I did it. And here's the thing. Do I really expect you to write times -1 every time? Well, no. I mean, we can take a pretty quick shortcut and say, hey, you know what? This negative right here, that's going to pop out of here as an I right away. And then I kind of ignore the negative sign and I do what I've always done, okay? If I apply that same thing to the next one, so right here, I see the square root of a negative. So the negative, I'm just going to circle that and say I'm going to pull that out as an I. And now the square root of 17, if I want to try breaking that down into other perfect squares, well, there are none. That just stays as the square root of 17, so it's I root 17. Okay, and again, if you feel more comfortable breaking this down to -17 or -1 times the square times 17, and then saying, hey, the square root of -1 is an I because Mr. Jansen just told me that. That's how it's defined. And then the square root of 17 I can't really do, so that stays trapped. Okay. Same thing with the next one. Again, the reason I would encourage you to look at this and say, hey, the square root of a negative, all right, that's an I, is because maybe you're looking at this going, hey, you know what? I'm feeling pretty good about doing this in my head. 18 is 9 times 2. The square root of 9 is a 3, and the 2 is still trapped. I don't know where I'm writing these things. Square root of 9 is a 3, and the 2 is still trapped. And look at that. Now I've converted that to a mental process. Okay. If you want to, I already took the I out, and now break that 18 down to a 9 times 2. Okay. Square root of 9 is a 3. The 2 is still trapped. Okay? And again, if you would prefer, again, let me start it over again. If you would prefer to say, okay, -1 times 9 times 2, and then start taking the square root. Say, hey, the square root of this guy is a 3. The square root of this guy is an I. The square root of 2 is just the square root of 2. Okay? We can still break it down that way. All right? But again, the more we can start to convert these to a mental process, the easier things are in the future. Okay? And I always just tell students, remember that negatives under a square root are dangerous because you can take an I out with that thing. And that's a terrible, terrible dad joke, but it's an easy way to remember that negatives give you an I. And then if I look at the last one, this is the trap question. Here's the cube root. The cube root of -125. Well, if we run all the way back up here and consult our list, 125 is on our list of perfect cubes. And so when I look at this thing, students are tempted to write the answer here as 5I, but that's not the case. The cube root of -125 is just -5. And so the idea here is the I value, the imaginary numbers, are defined by square roots. We are allowed to take the cube root of a negative. Because again, think backwards. -5 to the third power, -5 times -5 times -5 is a -125. And so I's don't apply to cube roots, okay? These I values, imaginary numbers, would only apply to even roots because we can't take the square root of something like a negative, okay, in a real world sense. But cube roots, fifth roots, seventh roots, negatives are okay. So don't fall into that trap. You can take the cube root of a negative. It just comes out as a negative number, okay? That's why we only have this special situation when we're talking about these square roots, okay?